So thank you for the introduction. I had a slide there, so I'll probably do it again. So yeah, at SpotHero, I'm a data scientist. My role revolves around building models, deploying them, doing business analysis, and also running experiments at SpotHero. And this talk will focus on the last part of it, the experimentation. Before I get into my talk, like who here has used SpotHero before? Oh, fantastic. Well, if you drove in today to Karlu and had a trouble finding parking, which I'm sure of, like, give us a try. So the agenda for today, I would be speaking about what is SpotHero, and then what problems are we trying to solve in this space. Then I will talk about a product feature of ours, which we are really proud of, dynamic pricing. And then I will cover different methodologies that we use to run experiments for this particular product feature and how we iterate on it. And finally, some key takeaways and learnings through a journey of running experiments at SpotHero. So with that, like, so we have 8,000 plus garages on our platform. Till date, we have done $1 billion plus in lifetime revenue, so that's great. And we have had more than 50 million cars find a parking spot. So the parking flow today. So like parking is not a cool and sexy thing. Like it's not that important. Like it's never the destination. You probably are going somewhere and maybe you need to park. So we sort of help solve that problem, but it's a stressful problem. Like when you leave, like you're always thinking about, okay, where I'm going to find the spot, will it be available, would I have to be far away? So there's a lot of stress in that as of today. And then once you reach there, you probably get a paper ticket, which you need to really save it. Otherwise, there are like fines at the end. And finally, once you check out, you probably pay. Like, I don't think it's cash anywhere now, but probably some places still do it. But most likely, you have to pay in some shape or form. So the problem with this is, let's say you prepaid for your parking and you could only like park for 3 hours, but you were running late, so you have to probably go back, revalidate it, come back. That's sort of not something you want. And then the problem is, what about if you're driving an EV car or you want valet, like you really don't like parking, like you don't have those sort of options because you don't know about them, and it's difficult to search about them if you don't know beforehand where you want to go. And finally, in terms of pricing, like it's a pretty old school industry. Like they have pretty flat prices. Like you pay $20 for 6 hours, and maybe there's a one flat rate, and there's nothing much going on over there. So with SpotHero, we sort of aim to change. Like we aim to change that. We have a pretty easy to use app. Like you can log in, find where you want to go, select your times, and then you can look at spots. So you can choose, you can filter like valet, EV, whichever ones you want. And once like you have finalized on where you want to go, the next step is you book it on a platform. And once you have done that booking, there's no need to like save a physical receipt or anything. You just have it with you. And then almost all garages have some sort of electronic gates. So you can just go in without touchless with the QR code, enter, park, and exit, with all very convenient. And by doing so, we were able to have a few benefits. Like it's transparent now. Now you don't feel that, oh, like I found a bad spot, is my car safe, or things like that. You beforehand know that, okay, you got the best deal possible. And also with this scenario, like since it's all digital, we are able to work a lot on the pricing aspect as well, which was not the case earlier. And pricing is what we will talk about today. So dynamic pricing. As I mentioned, parking was pretty old school. Like if garage owners wanted to know like what should the price of my spot be, they used to just walk around the block and see, oh, my competitor is charging like 20. I will just undercut him by $1 and charge like probably $19 or $18. That doesn't have that much science in it, but that was what was it. So like any data scientist, when I had a problem, like we built a machine learning model for it. And that is what we did in this scenario. We built machine learning models. And after building like 1 or 2 machine learning models, the problem that we came across was, okay, like this works. Like I checked my RMSE, we had some cool nifty things, and everything seemed okay. But the problem was pricing is a very nebulous thing. Like you don't know what is the correct price. Is it $15? Is it $20? Like you never seem to know, even though your models work, but finding that correct price is always really difficult. So yeah, so this is the summary of the problem at hand. We have drivers, we have garages, and we have built machine learning models that probably give different prices. And what we now need to understand is which model works better, because being a product company, we are always iterating on our models. We are building new stuff. Maybe we add new features in. There's some new cool technique. There's a lot of literature out there, and it's always very difficult to understand what works and what does not. So with that, we run a lot of live experiments on a regular basis, like to understand what works and what does not work for us. So if you have like experience running experiments, like these are some of the most common like strategies or methodologies, whatever you want to call them out there. There is a randomized like test and control, commonly known as A/B testing. You could probably do some sort of pre and post period testing, geolocation-based testing, and then there are 2 bit more not so common ones like switchback design and synthetic control. In the next few slides, I would be going over them and seeing which can work in a scenario and which cannot work in a scenario, and sort of seeing the pros and cons of each. So A/B test. I think everyone here must have heard or done A/B tests in some shape or form throughout their career. It's like the golden standard for like experimentation. If you're running experiments, you will hear about A/B test. And what it is essentially like in your entire population, you make 2 groups. One gets a treatment, other is the control, and then you release your new feature or whatever it is, and then after a certain time, you just check which group performed better, and from that, you make a decision which thing works better for in our scenario. So if I were to like bring that to the SpotHero context, we would have 2 algorithms. One part of the population would get algorithm 1, the other will get algorithm 2, and we would aim to understand which has a better impact on a revenue, profit, whatever that metric of interest is for us. So this is something that we want to calculate. For example, total rentals is a metric of interest. We have a control group, and essentially we would like to see a test either performing better or lower, and the green line is what we want to estimate, like this is a true impact. But it's not that straightforward. So like I mentioned in Marketplace, we had 2 groups, one algorithm 1 and other algorithm 2. Like probably they have different prices. And as is the case with prices, if let's assume one thing was cheaper, that would probably start selling fast. And it could have an adverse impact on the other group. Maybe they are not left with inventory now, maybe things are sold out. So that's not a true experiment to understand the impact. So instead, we measure something like this, which is an enlarged impact, which is not the case. So that little line over there is called cannibalization. I can probably do another talk on it. That's one of the key problems when running experiments in a marketplace, but cannibalization or network effects, this is something that happens quite a lot in marketplace scenarios like probably Uber, or maybe we had just started talking about DoorDash. I'm sure they would be facing similar issues as well. So A/B tests, we cannot do those in a scenario. Moving on. So pre and post, this is again a pretty simple technique. Whatever was happening right now, we stop doing that, move over to a different algorithm, and see does it perform better or not. Sounds straightforward, but again, it has some issues as well. So external factors, they play a pretty big role in a marketplace like ours, which is heavily impacted by weather. Like if it's snowing, it's raining, maybe there was a thunderstorm, no matter what the price is, like people are not coming out of their homes, so you really cannot test. And then there's another case of events. let's say Taylor Swift is performing like in Scotiabank Arena, like no matter what the price, your parking will sell. So it would be incorrect to sort of attribute your model to that success. It's just there was a big event. And then there's some internal factors as well that come into play. At a product company like ours, like there's a lot of experiments that are going on the same sample population. Maybe there is like some feature that has been changed, maybe some user flow has been changed, so that maybe could impact our experiment results. Then there are code outages, like at any tech company, like maybe some API went down or something else happened. Nothing to say about it engineers, they're amazing, but these things happen. So that has an impact on our experiment as well. And then finally, like marketing. Marketing plays a huge role in marketplace type scenarios. Like we spend a lot of money on Google ads, radio ads, and tons of other ads. So if there was a big marketing push, that could also have an impact on our key metrics. And that could also like pollute the results when comparing one algorithm to another. So this scenario, even though interesting, still does not really work well for us. Geolocation-based testing. Now this is an interesting one. So this essentially means that we take our algorithm one, run it in one city, take the other one, and run it in a different city. So now they're two separate cities. We don't need to worry about network effects or anything of that sort. And then after that, we just look at the results and see, OK, which one performed better. So there are something that we need to keep in mind. Obviously, like city A and B should be similar revenue. It shouldn't be the case that we are comparing Toronto with some small city up north in Ontario or something like that. So they need to be similar size in revenue. And they should be mature. Like it shouldn't be the case that you're rapidly growing in one city whereas you have matured in the other one. Like still, it will be difficult to get a read from the results. And finally, the start date and end date should be same so that we are able to average out things like weather, events, and things like that. This, even though is a good technique, but it doesn't work in our context. Maybe it could in a different scenario, because we are a rapidly growing company. Like it's very difficult for us to like find two cities that look same, like that have the same revenue numbers where we can do this sort of experiments. So this, again, becomes a little difficult for us. Moving on, switchback design. Now this is, again, a very interesting approach. Here what we are doing is, same city, same everything. We're just switching between algorithm 1 and algorithm 2 on a daily cadence, weekly cadence, whatever it is, but we are alternating over it. And the benefit we get over here is, since at a given day, hour, or time, like whatever the time is, like no two groups of population have a different set of algorithm. Everyone is on the same, and then the next day, everyone switches to the other one. So there is no network effects. Again, since we are alternating, we don't need to worry as much about the other confounding factors that we discussed, like weather or code changes or other experiments running. Hopefully, by law of large numbers, like we hope for them to like average out. And it's easy to implement. That's very important. Like we do not want to like waste engineers' time in like changing APIs and this and that. So it's easy to implement. So this is something that we chose and we use like till now to run experiments, release code changes, make changes to algorithms. And there are some questions that if you are running this at your company, you might need to ask yourself. So the first one is, what geographical granularity do you choose? So do you want to switch back on a city level, on a neighborhood level, on a national level? It might differentiate depending on what business it is, where you are currently. And then, like what time granularity do we choose? Like do we switch on like an hourly basis? Do we do it on a daily? Or is it on a weekly basis or something else? Like this would depend upon how your sort of business looks like, how much variability there is going from one time period to the other. Is it stable or not? Something else that you might want to look at is when running experiments is how long do you want to run it for? uh, a day, a month, probably longer. I would not recommend, but maybe it requires in your scenario. And then what type of randomization do we do? Like, there are many ways we can randomize. Like, what I showed was an alternate strategy, one day one, the other day the next. But imagine if you have like multiple cities, you could have a random order where in 2 days you do one method, then 3 days something else, and in a separate city you do have a different order, and then you average everything up to sort of see the results. So there are multiple ways to go about it, and one can choose depending on, again, the business metrics and how your business is doing. So at SpotHero, we ran this experiment on per city basis. So we take a city, and then our interval is daily. So we don't do hourly or anything less than that, just because there's a lot of variability in parking, like going from morning to evening. The number of orders or revenue like varies rapidly. So we switch in blocks of day, and then our randomization is alternate, one day on, one day off sort of situation. And then the measurement method that we use is a normal t-test, nothing fancy. Like if you're doing something like conversion, maybe we can use some sort of regressions to understand the impact, but I think t-test is a standard practice in the industry. And yeah, this technique has served us well till now. But I would like to talk about one other thing as well. Like this is a synthetic control matching. This is more of a technique that's still used a lot in social sciences group. I think now, in the last couple of years, a lot of tech companies have started using it to run their experiments as well. One of the earliest examples I could find was, like this is basically an intervention-based testing, which means like it's not possible to randomize or do anything like that. It's like you have to change. So one of the first earliest examples I could find was in California, they introduced in the 80s or 70s, they introduced a health tobacco tax, which essentially increased the prices of cigarette by 25%. And statisticians and social scientists obviously wanted to understand what impact does it have, and they wanted to run an experiment. But as is the case, like you cannot really run an experiment with tax. Like it's implemented, like that's it. Like you cannot go back from it. So this technique was used to sort of estimate the impact. And the way it sort of works is you create a synthetic city. You create a random city which sort of looks exactly like your target city, and then you do the comparisons. So if I were to put it in equations, suppose we are modeling the rentals in Chicago. We can write that as an equation like 2,500 like I've there, plus some percentage of some city, plus some percentage of the other city, and we sort of create a synthetic city out of it, which closely mimics our original city. And then once we launch our whatever intervention we want to test in a target city, we can then compare it with a synthetic city to see how much did it differentiate, something like in this graph. So this is something that is really interesting, and we, maybe in the next iteration, we really would like to implement it. And yeah, that's sort of about it. So in terms of summary, like we have discussed around 5 experimentation strategies, like starting with A/B test, pre-post, geolocation, and then synthetic control and switchback. So in terms of marketplace, like the first 3 strategies are still good, but they do not work as well when testing in a marketplace scenario where the changes sort of have an impact on the other group. So, and the technical implementation, as you can see for each of them, they are pretty much out there, so it's all green, so it's easy to implement. And yeah, that's some key takeaways in a slide. Like experimentation, we as a company found really useful. Like it sort of helped us get from like a feature delivered scenario to more to celebrate like value delivered. So that was something, and I really hope like that's the one thing that if you take away from this talk is that like running experiments to prove sort of the value of all the models and whatever you are building out there. And in terms other takeaways, like always have a target metric. Like I think whenever we are building machine learning models or anything, any model, like we probably get too bogged down with like RMSE. Like those are offline training is very important, but we need to have like a business metric that we're intending to solve. maybe we want to reduce a customer service request or something of that sort. That's very important to have when you go about building any data product. Then have a hypothesis. It's easy to say that we want to improve it, but it would really, really help you along the way if you can probably put a number on it, like, does it improve it by 5% or 2% or 3%? Because a statistically significant result in a t-test like really does not mean anything if you don't have like a good effect size. Like you can be statistically significant and have an effect size of 0.1%. So that doesn't really help you and all the effort that the team has put in. And finally, simple is better than complex. So if there's a strategy out there that is too complex, it would probably be difficult to implement in the first place. And then your stakeholders might lose interest because it takes a lot of time. So I think keeping it simple and focusing on the value delivered is one thing that is super important. With that, I conclude the talk. Thank you for your time. Are there any questions that I can answer?
Thank you for the presentation. I appreciate it. And also, I have a question regarding what features do you use in the dynamic pricing model? Like, do you use the driver's demographic features or the garage information? And among all those features, what are most important ones, if you don't mind sharing? Thank you.
Thank you for the question. So I use the word customized pricing there. I intentionally did not put personalized pricing. So no, we do not, if you go on the app and some other person goes on the app, we do not distinguish between like, oh, you are a rich guy and like, well, probably charge you extra. So we do not use any driver information. The information that we use to price a spot is definitely like what type of garage it is. Like, is it a valet? Is it covered? Is it not covered? What time are you going in? If you're going in like at night, let's say at 10 p.m. and the garage is empty, it really doesn't make sense for you to pay a premium on it. Like how long will you stay? So those sort of features. So we have like customized pricing like for each hour of the day and however long you will stay. But no, we do not use any, we do not discriminate on the basis of like what sort of like driver you are, like do you drive an Audi or a Nissan, like we do not do any like machine learning on that.
Hello, thank you so much for your time. My question is that in your experiment, how do you take care of the fact that some customers might be just transitory, some might be like more dependent on your product. For example, if they use it to park near their workplace, they might have they might have a slower delayed response compared to those that respond quickly because they don't have any commitment to that.
Sorry, could you speak a bit louder? I did not understand the question.
Sorry?
I did not understand the question.
I'm asking, how do you control between the two kind of customers, for example? One is like have to commit to that location, and one is can switch quickly.
So are you saying that?
I'm saying a price change might have some quick response for some customers. For some others, they kind of have to commit to this, and they might find alternatives in longer term.
Okay, so you're saying if a customer, if I understand your question correctly, like there's a customer and they like see a different price, like let's say log in today, they get a different price, and tomorrow they come, they get a different price. Is that the question?
Oh no, I'm actually asking if, for example, I'm going to work and I'm paying this much for the parking. Tomorrow I have to go to work. I'm not going to have quick response to the price change. Do you take control of that?
Sorry, let's probably connect afterwards. I'm unable to like.
Okay.
Yeah, sorry about that.
Thank you for your presentation. Can you hear me clearly?
Yes.
Yes. So I was just wondering for switchback testing, the event example that you gave, very good example. there might be a day when the event tickets go live, and on that day, the algorithm that is in play in your app, that might get the more number of rentals or the more revenue. So how does switchback testing, kind of compensate for that compared to the other methods?
I would, it's not perfect. So our aim is to reduce the impact of confounding variables and the network effects as much as possible. Yes, if there is an event that happens, and this is more of a SpotHero thing, but we do have something called event rates. So if it's a big event and it's registered in our app, on the back end, we sort of mark those prices as event prices, and we sort of exclude them from our experiment results. So, but definitely, maybe for example, the Scotiabank Arena example I gave, Taylor Swift singing, and so all the people parking in the Scotiabank Arena would have an event rate, but person could choose to park someplace else, and that rate will not be marked as an event rate, but it should have. So there are those sort of inconsistencies that come in, but we try to circumvent them as much as possible, I would say.
Thank you.
Yeah.
Hi. Thank you for the presentation. I have a question slightly different from the testing, but more about specifically the kind of features you guys are using for your pricing. How much does competitive pricing come into play, specifically because in your space, things can change very fast, especially if there's an event, other places start selling up pretty fast, so you start seeing an uptick in demand on the app, but taking into account competitive pricing, how fast do you guys react to that? Is it possible? Just because the reason I'm asking is you might have competitors who don't publish their rates, you can't find it online, can't find it anywhere. Like I said, you use an old school technique of people just used to walk around, just look at the pricing. How do you guys kind of work on that?
Okay. So yeah, so there's a model that runs on a weekly cadence. That's also develops our base rates, and that's the model I was describing, all the features they take. But there's a different thing that we do almost every hour. We do have an airflow job that sort of kicks, and we look at the rate of change of sales, whether there's an uptick in certain area compared to the other area. We look for those sort of inconsistencies, and we try to sort of be ahead of the curve as much as possible. But there are definitely things that we miss, and yeah, and your first question also, you mentioned about competitor price. If it's not there on the app, we don't know about it, but since this is sort of a marketplace, and a machine learning model sort of learns the nearby area as well. We look at the converted search data, so we sort of do understand that if there's a particularly high price that is not converting, our model does not predict that price. Whereas there's a really good price that is converting, all the other facilities which are using our model sort of learn about that. Did that answer your question?
Yeah, thank you.
Okay. Thank you so much, everyone.
Thank you so much, Amish, for that wonderful talk.